instruments for spaceflight. He's also the project scientist for the Volatile Investigating Polar Exploration Rover, or VIPER, which we're going to hear a lot about. And he completed his PhD in atmospheric, planetary, and astrophysical science at the University of Colorado, and has served as a PI manager for La Crosse, which also went to the moon, and the ENVIS instrument, which is an instrument for the commercial lunar lander, and I believe is on the VIPER rover. So these are just a couple snippets of the many different projects that Dr. Colapreti is involved in, and we're going to hear a little bit about VIPER, so take it away.
Thank you very, very much. And this whole session was, I think, organized really nicely, going from kind of a top level where Clive gave us a big picture, Barbara talking about the activities and opportunities and future missions, and no pun intended, I'll be drilling down into VIPER, which is one of the larger upcoming rover missions. It's not the only rover mission. There's a mini rover called Moon Ranger that Astrobotic has on the Maston mission going in 2023, but it is the largest of the rovers. So I'll just jump right on in. So as you probably can gather from the previous talk from Clive and Barbara, there's been really a revolution in our understanding or appreciation of volatiles on the moon. Back in the Apollo era, we saw there was some water, but the general belief was it was pretty dry, bone dry. Well, that all started to change with a couple of experiments in the late first decade of the late 20th century, or 21st century, with the LCROSS mission and the Moon Mineralogical Mapper, where there was water detected on the moon. Actually, another fun fact, I like using the fun fact that Barbara did, there was actually some ground-based observations dating back almost 8 years earlier that were deemed unpublishable because it was just insane, that showed hydration at the south pole of the moon. And at the time, the author couldn't get them published because all the reviewers said this is just ridiculous, but turned out to be true. So what the next steps really are, though, is to get down to the surface and understand the distribution of water, its state, its physical state, and its association with the environment at scales that I call the human scale. And that's what VIPER's really all about. So this is a bit of a summary slide up front in case I don't get to the summary. VIPER has been in development, if you will, for about 10 years, on and off, on and off, on and off, with various instantations, but I'm really pleased to say we are really on our way here now. We passed our critical design review just a couple weeks ago, which is fantastic. We have confirmed our mission area and had that approved by SMD, and we are on track for a November 2023 launch. This just shows where we fit within the Artemis program. You've seen this slide before. We're one of a number of assets, surface assets, that will be supporting Artemis and SMD and the science community in general. And we are one of the, I would say, the first reconnaissance missions to really pave the way and be a pathfinder for future missions to the South Pole. This is a quick summary. You saw Barbara talk about where missions are going, CLIPS missions are going to the moon. This one focuses on the South Pole right now. These are there are other missions going to the South Pole, but these are the confirmed landing areas for these missions. I showed the LCROSS impact site just for reference. You see the Maston 19C. 19C is the task order that they're contracted under, going near the crater Haworth. That's a large blue crater there to the right of it. And then Prime 1, you heard Barbara mentioned another drilling opportunity. That's the Prime 1 mission going along the connecting ridge between the Shackleton crater and Degarage. And then you can see the VIPER site up there to the upper right, and I'll speak a little bit more to that in a minute. But what's great about this is as I saw this developing, working with the various teams on these missions, you can see we're starting to develop a real survey of the South Pole. This scale bar to the lower right. This is critical. There's this is the topographic map of the South Pole. You can see there's just as diverse topographic relief and equally as diverse environments that we are sampling with these missions. So first and foremost, Viper is about understanding lunar water. It is both a science and an exploration mission. Of all the scientific endeavors with the greatest overlap, I think understanding volatiles of the moon is one of them. That is the overlap between exploration and science. And as I mentioned, we've learned a lot over the last 10, 15 years. Learned that there is water, that there's superficial water in the form of ice, there's buried water, there's also a lot of other volatiles associated with these dark, cold places. But we really don't understand their association with each other, meaning these various reservoirs, as Barbara mentioned, they don't correlate well, at least they don't seem to. We don't understand their distribution at the scales we think they might be governed at, smaller scales of tens of meters. We need to understand that. So that's what Viper is all about, is really prospecting for water at the poles and taking those next steps in the program to fully understand lunar water. So Viper had its instantiation as an exploration mission. It started actually in the human exploration side of NASA and now resides within SMD happily. And so it was conceived as really an ISRU, In-Situ Resource Utilization Exploration Mission. And so this slide speaks to that side of the house, if you will. And you have the classic lunar, or classic exploration processing chart to the right there, where you go from inferred potential resources through exploration, you get to approved reserve. The red box indicates kind of where we're working at right now. To the left, you see the critical observations needed. We need to understand the distribution, the physical state, and the context and correlation, meaning where is it? Is it buried? Is it on the surface? Is it associated with temperatures of only a certain range? Is it associated with certain geological features, geomorphologies, et cetera? So it really boils down to the distribution, physical state, context, and correlation. Now, this is all true for exploration, but it's entirely 100% true for understanding the science, too. Barbara put it very well. I used to get frustrated when someone would say, I just need to know where the water is. Well, you can't do that without doing the science. You need to do exploration science so that you can have this predictive capability. And so it's really a win-win. We're going to understand the origin of the water on the moon, as well as how to better predict where it might be. And those are the two level 1 goals for Viper. So where are we going and what are we doing? So we don't know where the water is, especially at scales of meters or tens of meters. So we're taking the first steps to understand the environments and the correlation of volatiles with those environments. And you can do this a number of ways, but the way we approached it is knowing that temperature is critical. You're not going to have water if it's too warm. We looked at the predicted environments where water might be stable. Again, these are predictive environments. We don't have measures of subsurface temperature. We have measures of the surface temperature from orbit at 250 meter scales, but we have very good thermal models, and they've been correlated with those surface temperature observations, so we have confidence in them. We've used those temperature models to derive maps of what we call ice stability regions. We've divided the maps into surface, shallow, deep, and dry, and they're defined here. They're basically defined within the top meter here. This has some exploration push to it, meaning they don't want to have to dig deeper than a meter if they don't have to. It also has some remote sensing throwbacks to it. Neutron spectroscopy from orbit that senses that deeper hydrogen only senses to about a meter, et cetera. So to the right, you see a figure of the Nobile region where Viper will be going. Red areas show areas of superficial water stability, meaning these are permanently shadowed regions where the temperature is always below about 107 K. Water should be stable there at that surface over geological periods of time. And then you have yellow, green, and gray areas. Green means in the top 50 centimeters, those temperatures are predicted to be stable to harbor water. Yellow, 50 to 100 centimeters, and gray means in the top meter, temperatures at some point over an 18-year lunar cycle get above the temperature stability point. These are the places that Viper will be going and characterizing. That's the one thing I should make really clear is Viper is a mapping mission. We're not just going to a place to study a rock. We're going to these areas and then conducting extensive mapping campaigns of these areas, much like you would do with terrestrial resource exploration. This is the Viper landed segment, the Viper rover. I won't go through all these various callouts, but just to point out a couple things. One, it's boxy. You know, boxy is good, right? Little Volvo commercial. The vertical panels are something that people may not be accustomed to. Barbara mentioned this, that the sun is always low to the horizon. And actually, during the Viper mission, the sun rarely gets above 5 degrees above the horizon. So the panels are vertical and on 3 sides. That way, no matter which direction we're driving, we have sun on. The wheels are a four-wheel independent suspension rover system, very different from the Mars rocker bogie 6-wheel systems. This allows these wheels to go up and down, turn, and go in any direction. This was done after extensive trade and consideration of the unique environment of the poles. It is unlike Mars, it's unlike anything we have on Earth, and so this extra capability was believed necessary to minimize risk. It is stereo driven. We use stereo cameras, and you see the mast coming up there and a radio antenna on top. It is a direct-to-Earth communication rover. We talk constantly to it from Earth. We do not use a relay satellite. In a minute, you'll see why, what limitations that has to it. But the fact that it's solar paneled and direct-to-Earth communications makes it relatively simple in its technology and keeping the price overall down, the development period overall short. This just gives a sense for the scale of the rover. To the far right there, you see it compared to some of the other rovers. It's at the CDR, we have a full-scale mock-up I'll talk about a little bit later. And once you stand next to it, you appreciate how tall it is. The mast, the top of the mast is about 2.5 meters above the ground. So it's a fairly large rover. These are the instruments that Viper will be carrying, and in the backup charts I've got some more specific details, but I thought this would be more appropriate here. There are really 4 instruments we carry. 3 of them are on continuously, while driving, while drilling, all the time. And this is very, very unique, and we worked hard as a science team to make sure this capability was retained. So the rover is power positive with all these instruments on, driving all the time. The first one is a neutron spectrometer system, similar to what's been flown in orbit. It actually will measure, it's the bloodhound, if you will, of the rover. It will be measuring subsurface hydrogen down to a meter continuously while roving with about a 1.5 meter footprint. The next to it is the near-infrared volatile spectrometer system. It's a near-infrared spectrometer system that goes out to, again, past 3 microns to 4 microns, measuring the water ice fundamental band, but also a number of other volatiles, CO2, methane, ammonia, etc. It also has a multicolor context camera and a thermal radiometer that measures surface temperature. Again, it is on continuously making these measurements. And then last is a mass spectrometer, M-Solo. It is a mass spectrometer that runs from 0 to 100 AMU. It will be measuring, of course, any gases that come up, but also making key isotopic measurements. Excuse me. It is on, again, continuously. I keep saying that because this is really unique. This is going to provide this incredible data set that we just don't have for the moon, or many missions for that matter. And then lastly, we have the Trident drill. This is a 1-meter percussive augering drill that brings up samples to the surface that both NERVIS and M-Solo will be able to observe. We'll be able to see the solid ices, volatiles in that sample, and as they sublime and evolve, M-Solo will be able to measure the concentrations that come off of them. Also, Trident has 2 temperature sensors in it, and we have specific operations where we will pause and measure subsurface temperatures. So these will be the first subsurface temperatures since Apollo and the first observations in the polar region of the moon. So that will be critical in validating our models of the subsurface temperature regime. This is an overview of the Viper mission phases. Again, another unique aspect of astrobotic, and we've heard this mentioned several times, Viper, you've heard this mentioned several times, is the involvement of the CLPS program, the Commercial Lunar Payload Services program. Viper is flying on a commercial landed service lander provided by Astrobotic. You'll see a graphic here of it in a second. So the first portion, that bluish portion of the mission, that's not NASA's mission. That is Astrobotic's mission. And it's a really different paradigm, which is fascinating and exciting and just really changing the way we do business, actually. Once they get us to the moon and the ramps go down and we drive off that lander, then it becomes the NASA Viper mission. And you can see the entire surface operation indicated by the green is broken up below it in various yellow chunks, legs and hibernations. Legs are when we have view to the Earth and sun, and that I call these working days. Those are when we're driving around, we're conducting operations. Because we're independent of where we are on the moon, the Earth at some point sets at the poles, sets below the horizon, and we lose our direct Earth communication. So what we do is we go into a hibernation mode and we park someplace that's sunny, that has minimal shadows, and we wait for the Earth to come back up. Once the Earth comes back up and we have sun on us again, we continue driving, and we do this for multiple lunar days. This is the lander that we'll be going on. It's called the Griffin lander, built by Astrobotic. It does also have a retroreflector on it, but we are the primary payload for this mission. It's as you can see, the rover will drive down either direction off the ramp, and you'll see later on I've got a photo of actual testing with a mock-up of the lander and rover that's being done at Johnson Space Center. It has been going on for some time. So once we rove off the lander, we get into what we call our prospecting mode. And that's basically, as I mentioned, we're driving and taking observations. And what we do is we drive to a particular ISR, ice stability region. We have within that region, a science station. Then within that science station, we do some rastering. We just drive back and forth, back and forth, back and forth. And while doing that, we have our instruments on measuring the subsurface hydrogen, any kind of gases that come off by the mass spec, measuring temperatures. And so we'll have this be able to fill in this map using geostatistical techniques of all these variables, building strong correlations, associations with the environment and the volatiles present. In each of these science stations, we have at least 3 drilling activities, and these are 1 meter deep drilling activities. And during drilling, as I mentioned, we observe cuttings coming up from the subsurface with M Solo and Nervous. The way the drill works is it goes down 10 centimeters at a time, that we call that a bite. It brings it up 1 bite at a time, brushes that bite off into a cuttings pile, and both spectrometers get to observe it. They'll observe any solid volatiles as well as gases, and also measure the temperature of the cuttings pile. We do this, as I mentioned, 3 times in any science station. What's great about being a real-time mission, excuse me, is that we as a science team get to make decisions basically on the fly and very near real time as to what we do with the rover when we're in a science station. Right now, built into the ConOps is that all 3 drill stations are pre-planned prior to launch, but the 3rd one is always assumed to be changed. And we'll change the location of that drill site based on what we've learned on the previous 2 drill sites. And so there's a whole new concept of operations being developed within the Viper Mission Science Center that actually looks at real-time science operations. And going back to the Apollo era, how did they do it then? What can we do now differently? And how is it different with a robotic mission as opposed to with an astronaut? But there's a lot of new learning we're doing there, and we're going to learn a lot from conducting the Viper mission in this way for sure. So where are we going? Recently, I guess a couple months ago, we proposed a mission area to Thomas, and he approved it. We're going to the Nobile site, which is shown in the upper right there in this context of the South Pole. The background is hydrogen abundance as measured by Lunar Prospector. There's a number of constraints that I listed there on the left as to what constrained us where we could operate. One, we wanted to go someplace with relatively high water equivalent hydrogen. That's a background map. We didn't want to go in one of the green or blue areas. We wanted to go to a place with a variety of thermal environments. And that's shown in the upper right, the red and the yellow and the green. Again, as I mentioned, we didn't want to just go and find hey, there's ice here, drill here. That'd be great, really interesting. But it doesn't help you as much as if you visited every place, including the places you expect not to find volatiles. I personally believe we're going to be surprised. We're going to go to a place where we didn't think we're going to find volatiles, and we're going to find volatiles. That's my personal belief. And then we need that's kind of the science, constraints on where we want to go. But then there's some practical constraints. We need periods that when we're in hibernation, when the Earth is down, we're in areas with relatively short periods of shadow. And just as there's places where there's permanent shadow at the South Pole, there are places that have persistent sunlight. There's no place with permanent sunlight at either pole of the moon, but there are places with persistent sunlight where the shadow periods are just a few days or even less apart from each other. We call these safe havens, and these are the areas we drive to park while the Earth goes down, and then our thermal system can withstand the 2-3 days of very, very cold temperatures. And those yellow blocks there show areas where you have less than 50 hours of actual shadow period. So they occur periodically across the South Pole of the Moon. And then, of course, we need an unobscured line of sight for Earth communications while operating. As I mentioned, every 2 weeks or so, the Earth sets at the poles. So we're going to lose communication without a relay regardless. After a lot of study, consideration of multiple sites, the Nobile site proved to be the best in terms of total operations and science return. Now, this just shows a little bit of a little bit better pictorial view of the Nobile region. This is actually images taken from the Viper planning tool, which will be planning all the traverses and everything in 3D here. The red areas are permanently shadowed regions. I've got kind of a scale bar to the right, but where you have the Viper lander indicated right there, the PSR just to the right of that is about 800 meters across. It's a fairly large PSR. It's dated back to about 3.8 billion years old. All these PSRs actually are quite old, and that's one of the reasons we're interested in going to them. We're actually interested in going to PSRs of different temperatures. Not all PSRs have the same temperature. They're all cold, but not all. Some get warmer than, say, for example, 50K. We're interested in 50K because that's where CO2 is stable. Some are colder than that. Some are younger, some are older. So we're going to actually visit a number of permanently shadowed regions to understand what's going on with each of those. Let's see, this just shows actually kind of a view of that PSR I just mentioned, the larger one, with the ice stability regions mapped over it. These ice stability maps have been generated on a 1-meter digital elevation model that we produced with LRO and narrow angle camera images. This is a new technique called shape from shading. So the craters and the stuff you see down there in the bottom with the rover, that's not a computer graphic generation. That's actual real lunar surface data. The data is that good from the Lunar Reconnaissance Orbiter that we can generate these DEMs down to that resolution now. And this shows the broader operating region. You see the yellow pixels now are these safe havens. And you'll see I'll show a traverse plan here that shows us scooting between them. So we explore all three of these PSR areas over the course of the mission. This shows a example of a traverse. Right now we've selected our mission area, but we're still refining the mission traverse. As I mentioned, since we're a real-time mission and we have developed these concepts of operations that allow us to change what we're doing midstream, this is true of even the Mars rovers, of course. The traverse will always be developed, being developed, being evolved, etc. So this is just a snapshot in time of what the current traverse is. You see some statistics. The green line showed the traverse path going to the various PSRs. Some statistics here. This is approximately a 106-day mission. There's about another month worth of extra mission that we didn't plan, that we see we can plan now. It goes about 27 kilometers total drive distance in that time, so we're pretty sporty. Our drive speeds, though, however, if you see those are our average drive speeds, are about 0.8 and 0.6 centimeters per second, so we're not that fast. That's the average drive speed. But what you can see is number of science stations. We go into a total of 12 different science stations at least, and each of those conducting 3 drill sites. So there's going to be a lot of drilling activity. We're talking about 30 to 40 drilling activities over the course of this mission. Yeah, thank you. I'm about to wrap up. Thanks. This is a video. The little red arrow shows the rover position. Over time, the black, the gray and white are sun and shadow. So where it's sunny, it's lit, and you can see us. We just left a safe haven. We go into a PSR there, and we come back and we park it down at this safe haven. We're always in sun, waiting for the Earth to come up. Earth comes up, and we go down to these smaller PSRs down here, explore them. We go to that safe haven, wait for the Earth to come back up, and then we hightail it down to this PSR down here and do exploration. Each of those little blue circles are science stations. Each science station is about 24 hours long or so. So that's an example of about 3 lunar days or a 100-day mission that we will be traversing. I'll just end with a couple fun photos. This is a photograph down at Johnson of an astrobotic mock-up lander with the ramps and one of our engineering rovers called the McGrew, where they are practicing driving up and down the ramps, learning what they can and making design changes. Finally, on the left there is a mock-up, what they call the Build Pathfinder. Using 3D printed parts and other pieces, they've assembled the entire rover just to get the procedures ready for assembling the real thing. But I like the photo because you get the scale of the rover next to the person. Finally, you have a full-up thermal mock-up in a thermal vac chamber at Marshall Space Flight Center, undergoing thermal vacuum testing. The thermal system for a rover at the poles of the moon is quite unique, so a lot of work's been gotten into that. So the hardware's coming together. The flight instruments are actually being built right now. They're all being delivered early spring. And next year, those are the instruments right there. And we're moving fast forward to 2023. Thank you.
It's so exciting to see all the progress that you've made. We have a lot of questions, and I hope I can get to a few before the coffee break. So what are the life limits of Viper? How long is the mission?
The life limits is basically, ultimately, we're going there in southern summer. And so as we move out of southern summer into southern autumn, the shadow durations get longer and longer and longer. And we are battery operated, solar powered. So eventually we run out of battery and we can't maintain the thermal subsystem. The batteries get to 100 Kelvin and that's pretty much it. So we think we can get about 130. I'm optimistic we might get 150 days.
Great. And what form do you think the water what form do you think the water is in the Viper will sample? Do you speculate on its geological or cometary origin? And how hard do you think it'll be to extract? That's a lot of questions.
There's a lot there. I think, again, my personal belief, I think we're going to find water in many forms. We're going to find it adsorbed to grains. We're going to find it as physical ice grains as well. And exactly how hard it's going to be to extract will depend on its concentration and its form. But that's exactly the kind of questions we're after.
And the last question is, if we miss this current launch window, how is that going to impact your mission?
So, yeah, and because we want to go in the southern summer months, we could either go to the North Pole 6 months later or wait a full year and go to the South Pole 1 year later. But overall, some things change a little bit, but overall, the same areas we would still explore. Yeah.
And actually, I'll do one more question. What are some of the future plans for Viper after this first mission?
That's a really important and question to consider. I see Viper as a pathfinder. It is going to provide a data set that we don't have. We don't know what we're going to see in that. We're going in. I like to put it. We're going into it with our eyes wide open. We're not going to make too many assumptions of what we're going to see. But what we do see should definitely inform the next steps. And there has to be next steps. It can't be Viper and nothing else. Viper's going to answer fundamental science, but like any good science mission, it's probably going to raise more questions than it answers.
Well, thank you very much. And I'm sorry I didn't get to everyone's questions, but I want to thank all the speakers in addition to Dr. Colapretti for a great session on Loon. I definitely learned a lot. So thank you very much. So we're going to have a short break, coffee break. We'll regroup at 11:15 for the next session. Thank you, everybody.